Resonance. Let's draw the Lewis diagram for ozone, which is O3. Determine the number of valence electrons. Each oxygen has 6 valence electrons. We have 3 of them, so we have a total of 18. Start by forming single bonds between the atoms. 1, 2. So that takes up 4 electrons, so we still have 14 electrons to assign, or 7 pairs. Place lone pairs on the oxygen atoms to give each 8. Okay, so we have 2, 4, 6 electrons there, and then the bond here has another 2, so that's 8. And then we have the same thing over here. We have 8 valence electrons. Problem is we've used all 18, but we don't have 8 around the central oxygen atom. We just have 6. All right, 2, 4, 6. Let's try using double bonds to solve the problem. We find that we have enough electrons for 1 double bond, as shown in these 2 diagrams, but not enough for 2. These solutions each solve the problem, but which is correct? Which is found in nature? And by the way, here the shape is bent due to the repulsion of the lone pair of electrons on the central oxygen atom. So let's just count it up here. 2, 4, 6, 8, that's good. 2, 4, 6, 8, also good. 2, 4, 6, 8. Okay, so everybody has 8 valence electrons. Both of these solutions are valid and introduce us to resonance structures. When there are 2 or more equally valid solutions to the distribution of electrons in a molecule, a blend of all those solutions is a result. One way to think of this is that the molecule vibrates between the solutions at a characteristic frequency. It's resonance. Another is to think of the electrons as being shared between all resonance structures. Here's our 2 structures. So resonance structures are the average electron structures of a molecule that can be represented by more than one valid Lewis structure. For molecules with more than one possible structure, resonance is a more accurate representation of electron distribution that can be described by the Lewis structures, which show only localized electron distribution. One way to represent resonance is to superimpose the Lewis structures with dotted lines representing possible double bonds. So here are the 2 structures we found, and we can have a dashed or dotted line here, or one over here. But only one double bond between these 2 atoms here, right? You'll have a double bond here and a single, or a double here and a single here, and that's what those dashed lines show. Example 1. Let's draw a Lewis diagram for nitride ion. Well, the nitride ion has 24 electrons. Our diagram shows 24 electrons, but the central nitrogen atom only has 6 electrons around it. 2, 4, 6. So we want to draw a resonance structure so that the 24 electrons provide 8 electrons around every atom. And just looking at the oxygens, in this case, each one has 8. But nitrogen doesn't, so we're looking to draw some resonance structures. Try it and go to the next slide when you're ready for the answer. What we're going to do is take one lone pair away from one of the oxygen atoms and put it into a double bond between it and the central nitrogen. So that's going to be our first structure. And let me just erase that. And then we'll do that to the lower right-hand corner oxygen. So first we did that one. Now we're doing the lower right-hand corner, and now we do the lower left-hand corner. So let's just count the amount of atoms on nitrogen now. 2, 4, 6, 8. Okay, we're good. And all the oxygens also have 8. So all 3 of those are valid. Another way to show it, just on one picture, is put this dotted or dashed line on each one of the bonds. And that tells you can only have 1 double bond, though, and the other 2 would be single. Draw the resonance structures for the nitride ion. We need to have 8 electrons around each atom. So let's look at this first structure here. Oxygen looks good, 2, 4, 6, 8. This oxygen also has 2, 4, 6, 8, but it has 1 less lone pair than this one. And why is that? Because we needed 8 electrons around the nitrogen atom. So we have 2 here, 4, 6. So you needed that double bond. So putting that double bond right here means this oxygen only has 2 lone pairs. But that could also be drawn and hang on, let me just erase some of this so you can see it, with the double bond on the other side. All right, those are the resonance structures. So we have two structures for nitrite, and the way you represent that in one place is this dashed line here showing that the double bond can be either on the left oxygen or the right oxygen. Draw the resonance structures for sulfur trioxide. We have sulfur in the middle, and then we have the 3 oxygens surrounding it. Everybody needs 8 valence electrons. So this oxygen with 3 lone pairs has an extra bond, so that's 8 electrons. This one's same way. Now, how come this one only has 2 lone pairs? Well, to give sulfur 8 electrons, we need 4 bonds. So you've got a bond here, right here, another here, and then 2 more there. We have a double bond. So that double bond means the top oxygen only has 2 lone pairs, so it has a total of 8 electrons. And let's erase that so we can see, we can compare the bonds to the next one. Here we go. We could have this double bond either on top, lower left, or lower right. So we have 3 resonance structures. And we represent that in one picture by putting this dashed line on each oxygen atom. So that tells you you can have the double bond in either one of the 3 oxygen atoms.